yesterday I realized that was maybe a little bit too intense, no? So today I'm going to be more relaxed. So it's not, today is not going to be about truth, but about tell you more or less what kind of things one can do with this machinery that I presented yesterday. Okay, so let me just remind you of the dynamics that we were studying as an example. And so we have this diffusion part, which is a sort of exclusion dynamics, which was happening at rate CXB of eta, where eta is the configuration of particles, and CXB of eta was equal to 1 plus A eta x minus b plus eta x plus 2b. Okay? And so it was important that this type of rate satisfies something called the gradient condition, okay, which is some technical condition that makes life easier in the terms of hydrodynamic limits. And on top of this diffusive part, we also consider a reaction part, which was and here we scale by n squared the diffusive part of the dynamics, and then this one here. So I use as an example the contact process type of the rate. And I claim that for this system we could prove a quantitative version of the hydrodynamic limit. Okay, so just to remind you the hydrodynamic equation. So let me write it in a slightly more canonical way. So this was the hydrodynamic equation, and u of u, well, if it was Laplacian of u plus au squared, it means that when you take the first derivative out, you get here 1 plus 2au. From here you see that this condition a bigger than 1/2 has also is also meaningful for the limiting equation. And f, well, f was some polynomial. Which now I forgot what it was. Okay, so it was some polynomial. U plus u. So f of u was u times
lambda 1 minus u times 1.
So this here was the hydrodynamic equation. And now what I want to explain is what can we say about fluctuations. And when I talk about fluctuations, I'm thinking about the central limit theorem around the hydrodynamic limit of this equation. Okay, because so the density of particles, which is some random object defined in some way, maybe by duality testing with test functions, converges here to some solution of a deterministic PD, which means that it converges to something deterministic. So this is what we call usually low large numbers, although it's an infinite dimensional complicated version. And then, well, if you have a lot of large numbers, immediately maybe one wants to talk about central limit theorems and large deviations principle. Okay, so for large deviation principles, of course, Jan is our local expert, and I think tomorrow you're going to talk a little bit about that, no?
Yeah, but tomorrow will be a physics talk.
Even better. But surprisingly, for this in this etapa, the central limit theorem turned out to be more difficult than the large deviation principle. I mean, it was we just proved the central limit theorem now, okay, this year, and the large deviations principle is known at least for some versions of this model since the 90s. Okay, so what do I call by fluctuations? So I'm going to define some field, okay? A field that I'm going to call xt n, okay, random field. And if it's a random field, maybe it's good to define it by describing its action over test functions. And here, so there was a 1 over n to the d because it's the density of particles, and there are n to the d sides, so it makes sense here to divide by 1 over n to the d over d. And then you make the sum over x. Remember that x runs here over the torus of size n. Okay. Okay, so we have to say run over the torus of length n. So the density of particles outside x is supposed to be close to this. Okay. Not point-wise, because this number is equal to 0 or 1, but in some average sense. So it makes sense to test again some smooth test function here. So this is the fluctuation field, and the theorem so this is what we prove with Otávio. Is that this field converges.
What is eta nx? Eta nx.
So here I have this process. Okay, so eta nx of t is equal
Eta
to
no, but what is eta n?
n. There is an n in the it's a scaling, no? So it's n is the length of the torus, and we are rescaling time diffusively, no? So this thing here converges, okay, to some random field xt. And what does this random field xt satisfy? It's going to satisfy the stochastic version of the linearization of the hydrodynamic equation. Okay. So the fact that it's going to appear the linearization of the hydrodynamic equation is very reasonable, because this thing here should be on a tube of size 1 over n to the d over 2 around the hydrodynamic limit. And so the equation that x satisfies is the following. So this part here, this is the linearization of the diffusion part, and then you have to put the noise. So that's the noise. And
So it is important that U is not a distribution.
it's important that U is not a distribution. It's very important. Yes. Yeah, in what you were proposing during the conference, you don't even know how to write down this equation. So here the noise is internal, no? And so in what you were proposing, the noise should be external somehow, no? And then you have to do the linearization of the reaction part, which is just this. And there is a second noise which comes from the reaction part. Okay? This function g here, it's a okay. So it has some expression. It can be computed in terms of the rates. Okay.
So if you start from equilibrium, then the hydrodynamic equation is trivial. Is that right?
Yes or no, because what is the equilibrium here?
Okay, so there's no equilibrium.
Okay, there is equilibrium, but I don't know how to characterize it.
Right, but suppose you start from it anyway, or
Okay, yes. But how do you know that this equilibrium has constant density?
well, suppose the system you change. I mean, suppose you remove the A and you remove the R. I mean,
Okay,
I'm
so
just asking a simple
here
question.
I'm cheating a little bit because actually you can see here that if you start with 0 particle,
Yeah.
you have 0 particle forever. So actually the only equilibrium of this equation is everything empty.
Why is that?
Because you have you always have a positive rate to die, and not always you have a positive rate to.
But suppose you start
Okay,
just
okay.
do the simple exclusion process and you start from equilibrium.
Yes,
So then the hydrodynamic equation is trivial.
it's trivial.
And so what would you get in that case? That's a special case of.
There's a special case, and okay, so you don't have this part. Okay,
Yeah.
let's forget about this one. Here you have a constant.
Right,
Here you have a constant.
right. So this is just the Einstein-Willenbeck.
Yes, the Einstein effect.
And if you make it asymmetric, then you get KPZ, or is that what?
Okay, so if you make it asymmetric, well, you totally asymmetric, we don't know how to do it.
Yeah, no, yeah, but what would you get if?
You will get the KBC. Okay, yes, but it is important that you start from flat, no? Because KPZ is not supposed to be. It's not supposed to be observed if the interface is not flat, right? If the interface has curvature, it's not clear what is going to happen.
So it's not known. It's no.
I don't know. I don't know if it's not known, but I don't know.
Yeah.
Because so for KPZ equation, after this titanic work of Martin and all the other guys, we know that you're going to get this covariant KPZ equation or whatever. But what is the long time?
Right, so this question doesn't address the long time. It does address the long time, right? Or does it not?
Okay, so it depends on this part here. No? But without this part here, this guy here should go to the right one, which is this end. So it addresses the long time.
So you get the 2/3 rather than the exponent if you do the asymmetric.
If you do the asymmetric, it's not what you expect, but we don't know.
No, I'm not asking that. I know it's a difficult problem. I'm just trying to understand what things mean.
Yeah. Here, I mean, if you are into it, you can put weak asymmetries and get extra terms, no?
No, but if you do the totally asymmetric, then
you
that is hard.
Then you should go to this KPZ fixed point, etc. But in dimension 1, of course, and then in dimension 3, it has been proved that the limit is this one. There is no KPZ equation in dimension 3. Dimension 2, I don't really know, because so this is conservative system, so it's not the same thing as the KPZ equation in dimension 2. Because this in dimension 1, this is the gradient of the KPZ equation, and that's something you can do in dimension 1. But in dimension 2, you have to take the divergence. It's not the same. No?
This log t to the 2/3 is that the 2D case? Or anyway, maybe sorry, I don't want to hold you up here.
No, it's okay. No, it's better. I mean, because it's nice to have this kind of discussion. So there is this work by Fabio Toninelli, no? That he was trying to get this anisotropic KPZ from the height fluctuation of the given model. They get log t to the 1/2, no?
Yeah, no, I just remember vaguely there's a paper by Yao and log.
Exactly. So this is.
But that's different. Or?
No, that's log t to the 1/3, yes. But which is not. It seems that it's not going to be KPZ, the KPZ that people are discussing now, because in the KPZ people are discussing now, what you get is log t to the 1/2. So it's another guy. Maybe not. I mean, maybe the variance for some strange reason scales differently from the scaling exponents of the model, which is very unlikely, but it could be. Okay, so this is what we get, and so this is not yet a long time, because it depends on the what happens with f, no? Because in this example, which is the contact process, there are two equilibria, no? There is one which is stable and one which is unstable. So the stable equilibrium is nothing, so not very fun. And the unstable equilibrium is the critical density that you can compute from here. Okay? Because you can check that f prime is positive. So this means that things are going to grow. So at some point, this process is going to grow exponentially. This rate grows exponentially in time, and at some point will go to infinity in logarithmic time, which is okay because at some point it has to find the other equilibrium. Okay, so this is what we can prove. And here something that is puzzling me is that we got this restriction here, d smaller than 4. Which is exactly the same that you get in many other results. I don't really understand whether there is a connection or not. But, no, of course, our theorem holds in this smaller or equal than 3, but really the critical dimension is really 4. There are various ways on what you can check that. No?
And so what is going wrong when t equals 4? There's one of the term is weird
So
now.
in the equation there's nothing wrong. The equation is okay in any dimension. Our theorem, so do you remember the theorem of the other day? We proved that the entropy, right, so h of t was less or equal than a constant. Here, since this process evolves in a finite time window, the fact that the prefactor here grows exponentially with capital T doesn't matter. But the next guy is the important guy, so it's d minus 2. Okay, there was these corrections in dimension 1 and 2, but let's focus in higher dimension to understand this thing here. Okay, so if you believe in this result here, you will be tempted to conjecture that actually the entropy should be bounded by 1, by a constant. Because, let's forget about this part here for the moment, okay? What I'm going to say is it's more easily understood if you look at only the first line of the equation. So this equation here, as you were saying, when u is constant, so when you start from the stationary solution of the hydrodynamic equation, it's just the Ornstein-Schellenberg process, and the invariant measure of this Ornstein-Schellenberg process is white noise. And we are comparing with white noise, right? That was our initial reference measure. And you are convergent to white noise, so you, in principle, you expect that the entropy should be bounded. So it should be the solution of this equation is absolutely continuous with respect to white noise for any positive time, whatever you put at the beginning. So you might expect that here, when you do this computation, you should get that in the limit you get. So the limit is absolutely continuous with respect to the reference measure. So at any time n, this should be of order 1. Okay, this is what you would naively expect looking at this equation here. But of course, this is not the whole story, because in this equation there are lower order terms, and those lower order terms they might be small, multiplied by some small constant depending on n, but they might be very irregular. So if they are very irregular, they will spoil this this bound somehow, and that's actually what exactly happens. So in this equation here, the next order correction term is a square. Okay, so it's this square term that appears in KBZ equations and friends, and that guy spoils the exponent in this fashion here. Okay, so that's just to tell you that this exponent cannot be improved somehow. I already discussed this the other day, but now if you what is going to compete here, what makes this d over 4 critical is the following inequality. Okay, so what is going on is that this entropy has to be smaller than the factor that you put in front of the field. So the field is defined here. There is 1 divided by n to the d over 2, and this factor here has to beat the entropy, right? So Why is that? So in dimension 1, this thing here shows that entropy is bounded. But if entropy is bounded, it means, from the point of view of the density of particles, that I can add to this field any constant I want. And by constant I mean any function. So if you have this field x and xtn, you can transform this guy here into stn plus h of xt, just using finite amount of entropy. Okay, and this ht here could be even random if you want. If you make it random, you cannot make it singular. It cannot be a distribution; it has to be a function. But it could be a random function. You can put, I don't know, a Brownian bridge there, for example, and that will cost you only a finite amount of entropy. Okay.
So this is Cameron-Martin theorem, or?
No, I mean, well, you could see it like that in the continuum.
Yeah.
But in this discrete, you just play around with your Bernoullis, and you shift the Bernoulli a little bit, and you check how many entropy you need to shift the Bernoullis around, and you discover that if you put you can put whatever constant function you want.
I'm a bit confused about what you're saying. So you're saying d less than 4, is that a technical condition or is that a real condition?
I'm not sure. It should be a technical condition.
Because in higher dimension, the fluctuation should be less, right?
Yes, but so the point is that what we are doing is we are comparing with product measuring. There's no in higher dimension. That's not a good idea.
Why not? Usually it's a better idea the higher the dimension, no?
Would it be related to the non-gradient method we were discussing?
It
5
will be
minutes
related
ago?
a little bit to that. Yeah,
So
but
you need to add corrections to be better?
you need to add and the corrections are the same actually. And so another way to see it is that if you look at this full equation, this term here is going to, okay, so if you don't have this noise here, you only have this noise here, then now it's the stochastic Hill equation, and the invariant measure is the free field, no? Well, there is a mass here, no? But maybe you can define your f in such a way that f prime is 0, and then you don't have a mass. And so the mass is not really helping you. So, and now the free field is very singular with respect to the white noise.
But I thought you were talking about large distances rather than small distances. In that sense, it's much weaker in 4D than in...
Yeah, but in 4D, we already passed to the limit. So, when you say large distance or small distance, I mean, there's still the scale is already fixed. I mean, the two guys are living in a space of size 5, and we know that at distance 1/4, the free field starts to show up. So the point is that under this condition, okay, when you have this, you can spoil the field in a way which is going to be considerable though from the point of view of the limiting equation. And if so, that imposes this condition d is smaller than 4. If d is equal or higher than 4, what you expect is that you have to compare with another thing. That's the point.
So, but the short wavelengths, they should know the short distances of this limiting equation, they don't really matter for the system, right? Or do they?
Yeah.
Because I thought if you're looking at t of order 1 or distances
Yes.
of order 1 in the macroscopic scale, then do you really care about the short distances of the macroscopic equation? Because
So let's say that you want to compute the variance of this guy here.
yes,
Then there's going to be a diagonal term which is which is of a size which is comparable to the other one. So if it's white noise and you compute the variance of this guy, all the variance comes from the diagonal term. So the only thing you care about is the short range correlation.
Just the last question. So of course, all the strategy has been devised to go non-equilibrium, and therefore the entropy bound is the best you can get. If you start from equilibrium, as you said, your measure is constant. Your HNT. So I mean, how can you make the most of it? Of the fact that you start from equilibrium in your strategy, if you see what
Okay, so the point is that if you start from equilibrium, it means that you go to something that also starts from equilibrium. So the limiting equation also has a well-known equilibrium, so everything is in equilibrium. So in that case, this strategy doesn't really tell you something new.
Mm-hmm.
And in fact, it is the equilibrium problem in particle systems is kind of well understood. If you know what the equilibriums are, and your dynamics has reasonable features, then you can compute this. You can derive this fluctuation result. But so this kind of a strategy is going. So it was developed for non-equilibrium systems, but also it could be useful in equilibrium systems on which the equilibrium is not known. Okay, because or maybe the equilibrium is too complicated. So it comes to my mind, for example, this KPZ equation in higher dimension. If you take the KPZ equation in higher dimensions, you don't know the invariant measure, right? Because this quadratic term will spoil, will mess with the invariant measure. And in the limit, you just want to prove sort of triviality, no? So you want to just prove that your equation goes to the linear equation. Then maybe this strategy can be useful, because the point is that in all of this business, somehow you know how the limit looks like at some order. That is what is going to allow you to define a nice reference measure. And now that you have a nice reference measure, you can try to improve your knowledge of your system going to the next level. Okay, so this is what we did here. I told you, well, the hydrodynamic equation is there. That allows me to define some nice reference measure, these product measures, which should be, at least at the level of hydrodynamic limits, should be a good approximation, right? Because, well, it converts to the right thing. And then you say, well, let's try to see if using this information, I can go to the next level, which is the CLT. And then the answer is yes, you can, using this zeroth order information you have about your process, you can go to the next order. And this is kind of a general strategy. Okay? This is something that might be useful in other situations. So,
I have another question. So you haven't rescaled time here, right?
well, I put the n there, so I actually rescale time in a diffusive way if you want to.
Okay, so this is t to the 1/2 scaling exponent if you want, but you have a more precise.
Yeah.
Would that be significantly easier to prove if you just want to know that the scaling exponent is 1/2?
Yeah, probably. Well, maybe yes, but well, it depends on the setup. You have to build the correct setup for that, no? But in principle, it could be. Yeah, because in that case, you don't really need to identify this constant, the square root of u, etc. No? You just need to show that this constant d there is finite somehow.
Well, I suppose you want to know the asymptotic anyway.
Yeah, I mean,
Okay, but it's the same order of
Yeah.
problem, roughly.
yes. Very good. So, I want to say. Okay, so let me maybe just tell you a little bit about how to prove this kind of things, because so on Monday I wrote down some inequality that I'm not going to write again, but maybe you remember I wrote down two different inequalities. One was the Gauss inequality, and there was another one that was there to estimate exponential moments of observables of your system. And it was a variational formula which looks almost identical from an abstract point of view to the Gauss inequality. Okay? So it means that if you know how to estimate in Gauss inequality the entropy production terms in terms of the Fisher information, you can do the same for this variational problem. Okay? So maybe I'll write down the variational problem, because probably you completely forgot about it. So the variational problem was this. So there was a function v here that was a function of our process. This was less or equal the integral between t of the supremum over f, and here f is a density with respect to the reference measure mu t. And here you have, so there was a minus this Fisher information was the integral of the Carré-Duchamp with respect to the reference measure, plus the integral of v plus 1/2 L star t of 1 minus dt log psi t. So this is what I call f yesterday. F mu t. Okay, so here the supremum is over all f, which are densities with respect to the measure mu t. So that was a variational formula for this, and you can use it for any function v you want. So yesterday we learned how to bound the integral of this function big F with respect to this density in terms of this guy here. That was what this the main lemma was doing. It was exactly that. I show it for a function v for the function f, which was a particular type of function, but actually it holds for any function. So you can add v to the mix and get some bounds. Okay. So when you look at the equation that the field x, so let me call maybe g the function because I put f there. So usually, since this is a Markov process, you can write any function of your Markov process as the integral of something, so usually, so it's the integral of the generator applied to the function, plus the martingale. Okay, so well, you do the computation, and after a while, if you do everything in the right order, okay, so this ls here that I put is just the operator that appears in this equation. Okay, so this equation has two parts, one random part and one deterministic part, and the deterministic part is just it's a linear parabolic operator. Well, maybe it's not homogeneous in time and space, but that doesn't really matter. It's still a linear parabolic operator that I'm going to call let's say ls, and actually this L that appears here is not that is a joint, no, because it goes to the test function. And so this part here is very likely to converge to the solution of that equation if I can prove that whatever else I got in this expression goes to zero. Okay, so you do the computation and you discover how this term here AD looks like. Okay, so in this particular example, with those rates,
So I thought there was no IT. I mean, it's just.
this is okay. So actually, here there should be L of XS. And what I claim is that L of x can be written as a linear part plus something else.
Okay, that's
And then you have to compute the something else. Of course, I mean, what I wrote here is just an identity defining IT, no? Because, yeah. And then you look at AT, and AT looks of the following way. Okay, so AT looks like this. So the structure, what is important about it is the structure. So this function h is something that depends on g, and depends on it's going to be some sort of error. Then it gets it has derivative of g and maybe Laplacians of g, etc. Also depends on u because u is multiplying g in this operator here. Lots of terms. But the main point is that this is a function which is bounded in space and time by a constant that does not depend on n. So it's a bounded function. And then also what is important is that here you have a quadratic term. Okay, so that what's important here, you don't have linear terms. If you had linear terms here, you could put them back here. So that's okay. But so here there is a quadratic, maybe there are cubic terms, etc. But they behave in the same way that the quadratic terms. So you have this guy here, and
So, actually, just to rephrase it in terms I know, so it's just a way, writing with L star is a way to close your equations,
yes,
and you move the part you want to close in the AT.
exactly. So all the garbage I'm putting on the 80, and 80 you can see, check that it is of this form. So, but now, I now want to prove that this guy goes to 0. But notice that here you really have to do something yet, because this is this for fixed time t, what is inside that is not going to 0, right? Because it's very reasonable that these guys are maybe they are not independent, but they are close to independent. So what I get here at best is the sum of independent random variables, and I'm taking Gaussian normalization of them. So this guy here at best is bounded, so it's not going to 0. So you really need to use the time integral to find extra cancellations here. And the way to do that is using this inequality that I got up here. Okay. So what you see that this guy here is of this form. Okay, for some function v, with v is this. No. You plug it into here, and you see that v, which is this, and f are of the same type. F was also of this form, no? It was also a sum of quadratic terms times bounded functions. There was not 1 over n to the d over 2, which is why this guy here is going to converge to 0. And this is the point at which, so this guy here, we know is going to be bounded by something of the order n to the d over minus 2, because of that was this lemma was saying, this main lemma was saying that the integral of a function with respect to f can be controlled by this part here with an error which is of order n to the d minus 2. That's what we proved the other day. And this order n to the d minus 2 is the one that has to be smaller than this d over 2 here to make this guy here go to 0. And that's the point on which this d is smaller than 4 condition appears. So it's very easy in the computation. It's just that without the guy here, okay, without this n to the d over 2, we know how to estimate this guy, and the error is going to be of order n to the d minus 2. Putting it back is going to go, now the error is n to the d divided by 2 minus 2, and that if this thing, that thing there goes to 0, then it means that this term here goes to 0. Okay? So, so if you apply again this, so if you apply the lemma that we proved yesterday, you plug it inside this variational formula with the function v, which is given by this expression here, then you can prove that this guy here goes to 0. Okay? Yes?
Actually, in which sense do you have convergence of that theorem? Is it for only for fixed t, or is it space-time object?
Yeah, so it's dimension dependent. It deteriorates with dimension. So in dimension 1, it's the nice result that you want to prove, that guy as a process in some solid space, etc. Then in dimension 2, the estimates start to deteriorate, and what you can do is that you see that the index on your solid space goes to like to minus 15 or something. Maybe I'm exaggerating, but
it's still space and time.
it's just space and time.
So that equation, the limiting equation makes sense in any dimension, or is there?
It makes sense in any dimension. And then so in dimension 3, you lose time. So if you're happy with the subspaces
What are these operations?
of negative regularities, things like that, then it's also space-time comparison. Okay. Of course, so most, I will say that most people will be satisfied with the following facts. So this thing here converges as a process. This guy here converges as a process. And this thing here converges to zero probability. Okay? So those are those three things you can prove more or less dimension independent of dimension. But this guy here is the one that spoils the space-time regularity of your convergence. Which kind of makes sense, no? Because it's the regular guy. No? Although this guy is very small, it oscillates like crazy. So I think no, I don't really want to enter into how you are going to estimate this guy using this lemma here, because then it gets technical very quickly. So maybe I just explain a few models for which we can say things which are meaningful. So in general, this strategy works well when you have a sort of parabolic equation with noise in the limit. Okay, so the fact that the equation is parabolic is very important. Okay, so if you don't have something like a Laplacian there, basically you don't know what to do. Okay.
Where did you use that?
So it was hidden in the main lemma when I talk about flows. So that the fact that you can transport in a nice way one measure to the other is linked to this parabolic character of the limiting equation. So it's exactly there that the parabolic character of the equation is used. Because if you don't have the parabolic, if you have only transport, then you cannot do this. You cannot transport one measure to the other, because there is one direction in which you go and you're going to escape. You're going to miss some region of the space. Okay, so.
But excuse me, it was not the way you did this transport part was not directly linked to the microscopic dynamics.
No.
Provided you could imagine something even weak or asymmetric, but which goes one, I mean, like P and Q, not totally asymmetric. Then you have all the direction, but still it would be a problem. So
there is some Hodge theory that you can you have to think about it, because so where this flow lemma comes from, it comes from the integration by parts. So you have your measure, and you start to see from your dynamics, so in this square here. So if you're in continuous time, which is where the structure is, you can explain it in a more clear way. This quadratic term here contains some germs. No? So you have your manifold, which is your configuration space, and here there are a lot of germs. Okay, so these germs that generate some forms. And this question that you're asking is whether these forms generate the space. Okay, so in that case, I can actually solve in an abstract way the transport problem. And so for that, what you need is hypocoercivity stuff, no? That if the germs that you get from here are allowed to generate the whole space, then it means that you can transport one measure to the other. And in that case, you can solve this flow problem, and then you're in business again. Okay? So, which still depends on having enough parabolicity there.
So hypoelliptic won't work? I mean,
Probably hypoelliptic will work. I mean, I'm not sure if I want to state a theorem like hypoelliptic works, but so Stefano Ola has been very much into this question, and he has ways to make it work. I mean, for concrete example, you have this. He works on these systems on which you have various conservation laws, and you put noise only on one of the conserved quantities, and then you want to somehow transport this noise to the other one, and then you need to do this hypoellipticity. So there is a slight difference between what Villani calls hypocoercivity and what people call hypoellipticity, no?
I don't know that difference.
Because hypocoercivity is a sort of effective hypoellipticity, because in hypoellipticity there are abstract theorems that don't really tell you how diffusive your system is. And in hypocoercivity you do know a little bit, so there is some epsilon somewhere that makes the thing strictly convex in some scale, and then you're into business. Of course, from our side of probabilities, usually what happens is that we start to average out until you get strict convexity. No? So in that terminology, we will more using hypocoercivity instead of hypoellipticity. But that's very important. So this is that's the continuum analogous of this of this discrete cute identity about flows. Okay, and also another remark about these flows, which I found very interesting, is that so recently Claudio Landin discovers that for non-reversible Markov processes, you can define capacities in terms of in terms of variational problems. So for reversible Markov chains, the capacity of a set is defined as the infimum of some Dirichlet form over test functions. And this is no longer true for non-reversible Markov chains. But what is true for non-reversible Markov chains is that this capacitor is the infimum, but now overflows instead of functions. So if instead of looking at the function, you take, so a flow is more general than the derivative of a function. And in the non-reversible case, sometimes the maximizing flow has some counter currents around to compensate the non-reversibility of the chain. So there is, in terms of flows, now there is, we have access to more machinery, even to deal with the non-equilibrium situation. What else I want to say? Okay, so just a quick remark. So there is a very simple model of non-equilibrium particle systems, which is when you take your favorite system, you can even put rates there for which you have nice product measures, invariant product measures, but now you modify it a little bit, so you consider a cylinder instead of a torus. Okay, so you put boundaries. Okay, so in dimension 1 you consider an interval instead of a circle. So in dimension 2 you take your torus and you cut it here, with scissors, and now you get a cylinder. In dimension D, you do the same, but of course I've never been able to imagine a 4-dimensional scissors doing some cutting on a 5-dimensional stuff. But anyway, you can put boundaries, and if so the rules basically is that if here they enter with rate alpha and they get out with rate 1 minus alpha. Okay, and here the same. When you have the exclusion process, these are rules. But if you have a little bit more interaction, you have to be a little bit more careful, because you don't want to mess too much with the systems. Otherwise, you create boundary layers, and then things are much more complicated. Anyway, so you put these reservoirs with some rules that make sense, and what happens now is that your system can be as nice, symmetric as you want in the middle, because alpha is different from beta. There is a current of particles from one side to the other. And now we don't know it by a measure, and unless your model is exactly solvable in some sense, or you cook up a very particular example, and then you want to prove the same kind of results. And we can do that, because we know that the system satisfies some hydrodynamic equation with boundaries. Then we know what are the stationary solution of that hydrodynamic equation. And now we can use data product measures with the stationary measure, with that associated to that stationary profile as the reference measure. And now there is no time, so computations get a little bit easier. And then you can repeat the same arguments, and you will get CLT results for this kind of system. Okay. And then you have some variants there, which are the ones that should be. Okay, with using the microscopic fluctuation theory, you can predict what equations are you going to get. And well, now we can prove that those are the equations that you get. Okay, I think maybe just stop here. Yesterday probably was too much, too intense, so today I wanted to make it a little bit lighter. So thank you very much.
Everybody asked all the questions they want to.